Hello all, welcome to section 14.3. What we're going to be doing here is we're going to take a look at simplifying some of these integrals that we're trying to do by converting to another coordinate system, so converting to polar coordinates. The reason that we would do this is that there's instances where either the function that we're trying to integrate would be simplified by switching to polar coordinates, or the region that we're trying to integrate over would be simplified by using polar coordinates, so like the region R in the xy plane. So I want us to look at one example of that scenario, well, I guess two examples here, where I've drawn these two regions up on the board, and I want us to think about how we would have to represent them using rectangular coordinates, but then how we represent them using polar coordinates. So actually a good idea would be for you to pause the video and try and do both of those. So the one is sort of two circular arcs, one with a radius of 1 and then one with a radius of 4, and then this one is a circle of radius 5. So think about how you'd represent them with polar coordinates. When you're ready, jump back on. When we're looking at the first one, remember polar coordinates are r's and thetas. So r is your radius and theta is your angle. So if we think about this one, if we think about first thinking about the radii that I would go between, well, I'm going to go from a radius of 1 out to a radius of 4. So R is going to spread between 1 and 4. If you think about what those curves actually are, remember R equals 1 is the full circle of radius 1 because theta just can swing and be everything, so it makes the full circle, and R equals 4 is the full circle of radius 4 centered at the origin. Now, I don't want, so then I just end up with the region between those, but I don't want the full circle, I only need a portion of it, so then we can restrict theta, where really I just need theta to swing through this first quadrant, so we can start with theta is 0, and then swing up to theta is pi over 2. Which is a very simple way then of describing that region, because all we ended up with was two sets of bounds that are both scalar bounds, so they both are constant, as opposed to, if we think about having to do this one with rectangular coordinates, whichever way we do it, right, if I try and do top curve, bottom curve, well, the bottom curve in this instance would switch here, where first we would have to do going from this circle to this circle on that first region, and then on the second portion of it going from this circle to the x-axis. So we would have to split our integral into two portions, and we would have to use like those little semicircle formulas for those guys. And even if I then tried to do the other way, we'd run into the same problem where my left curve would start as the y-axis and come to this portion of this circle, and then it would switch to being this portion of this circle coming to this portion of this circle. So A, the formulas would be nasty. Also, the region would need to be split no matter how we did it. Just not ideal, whereas the polar coordinates are much simpler. If we think about the second one, we actually did regions like this in our previous examples where we had a full circle and we went from like the top semicircle to the bottom semicircle, for instance, which was just not my fave. So instead, if we think about this again as r and theta, well, thinking about r, well, it goes all the way to the origin, which is r is 0, and it comes out to r equals 5. And then that full thing just swings all the way around for a full rotation, which would be theta from 0 to 2 pi. So again, a very simple way of representing the region, and it only uses numeric bounds. So when we do set up those integral bounds, they're both going to be numeric, which will be really nice. A couple other things to kind of recall when we're thinking about converting to polar coordinates, which I guess for the function itself, we're really converting to cylindrical coordinates, but remember z is just z. So whenever we have these z equals functions, it's still going to be z equals, and then it'll be in terms of polar. So things we can recall, try and remember these. If you want to pause the video quick, you can, or just say them along with me. We'll pretend like we're in class together. X, remember, is r cosine theta, and y is r sine theta. R squared is the sum of these two squares, so it's x squared plus y squared. And then tangent theta, well, tangent is sine over cosine, so it's going to be y over x. So those three are the ones that help us convert back and forth. And then what we're going to need to think through that's going to help us out a little bit is remembering back to when we did polar coordinates and we did areas between polar curves is going to help us out. So I drew a picture up here of, let's pretend we have two polar curves, so we have R1 and R2, and we're trying to find the area between those curves where that would be in between two theta values, which theta values are those angular values that come out from the origin. So we'd be looking for like that shaded region there. Now, when we created this integral, we thought about, well, rather than using representative rectangles, we would use representative sectors. So little circular sectors is what we would use for our representative regions. The area of a sector I have written over here is area is 1/2 theta r squared. You can think about, right, the area of a full circle is pi r squared. So in that case, theta would have been the full circle, which is 2 pi. So that's why it's like 1/2 times 2 pi r squared, which gives me what I wanted. What we're going to see then here is we thought about, well, if the sectors are my little representative regions, then the thing that's going closer and closer to 0 would be the theta values of those sectors. They're going to keep getting narrower and narrower. So when we do this integral here, we'd be thinking about it as being a d theta integral, because theta is going to be what's going to 0. And then what we would really have is we'd have like the kind of that outer area minus the inner area. So we would have like an outer area formula minus an inner area formula, which would end up looking like a 1/2 theta, which is d theta, and then r squared, which would be my outer r1 theta squared. I'm just going to pull the 1/2 out. So that would be like the full area from here all the way to the origin, and then we would subtract off the inner area, which again you can kind of factor out the 1/2 and the theta to just then have R2 of theta quantity squared. So I'm going to refer back to that formula in a minute here. In my next video, I need to clean off the board so that I can write one more thing. But we're not going to see this exact formula in the original formula that we're going to have for finding these regions. But we're going to see this formula show up in a minute to kind of confirm that our definition that we've set up is correct. So pause this video and then we'll jump on to the next one in a second here.